the last session we discussed about the integral form of Gauss's law, and now for evaluating the differential form of Gauss's law we are going into evaluating an electric field, a general electric field through a cube of side dx, dy and dz. Now imagine a space that is here and there is an electric field. Assume that there is an electric field and which is some E is equal to, we can represent it as E is equal to E x x cap plus E y y cap plus E z z cap. So that means the electric field has three components, E x, E y and E z. It is all over this space and it is in 3 dimension, and at this space and where the electric field is, at this space we are imagining a cube of side dx, dy and dz, and we have to evaluate the E dot ds, the so called flux over the 6 surfaces or the total surface over this total flux over this cube. That means we have to evaluate the E dot ds for all these 6 surfaces, the front surface, the back surface, the side surface and top and bottom. So we are going to evaluate that. So for evaluating that we are assuming a coordinate system, that is something like this, an x axis, y axis and a z axis. Okay, and this corner is at the coordinate x, y and z. Now we want to evaluate E dot ds. So for that, first of all we are considering the front surface. Okay, that front surface means one of its side is dy and the other side is dz. So we know that it has an area dz into dy. Okay, so this is our area and it has a side dz and dy. Okay, now we want to evaluate E dot ds. Let E dot ds for this area. So we know that E, expression of E already we have. Now we want to find the expression for ds. ds is equal to it's actually exactly this area, and this is a rectangle and which has side dz and dy. So its area is simply its product, that is dy into dz, but area is a vector, so we have to consider its direction. What is its direction? Again consider this cube. So this cube is a closed surface, and for a closed surface the direction of the area is always outwards, and also it should be normal to the surface. So for the front surface, this is the front surface, it should be something along this direction, or simply speaking, or let me consider another surface. For this side surface it will be towards here, for this top surface it will be towards here, for this side the left surface it should be something towards here, and so on. Okay, now we need only this front surface, so we are considering only the front surface. So for the front surface the direction is along here. This will be the direction of the area. So, and we know that from the coordinate system x coordinate is towards the back side. Okay, now the front surface will have a direction opposite to that of x, that is x is into the board or sideways like this. So then minus x cap will follow this direction. So minus x cap, so minus x cap will be the direction of our area because it is opposite to the considered x direction. So minus x cap is the direction of our area. So we can put that minus x cap there. So that is, I am putting the minus sign here and an x cap here. Now we got E, already we have defined E, and we have ds. So we are going to find E dot ds only for the front surface. So for the front surface E dot ds is equal to E dot ds for the front surface is equal to, take the dot product of this with this. We know that when we are taking the dot product, the like component only exists, that is x cap dot x cap will be exist as 1 and y cap dot x cap is 0, z cap dot x cap is 0. So x cap dot x cap is 1 and ex. So minus ex dy dz. there is no direction because we are taking the dot product. So, we got the value, the flux for the front surface only. Now, we have to calculate for other 6 surfaces also. Let us consider the next surface, that is again the same, we have the cube and the coordinate system, and now considering the back surface. Now, for the back surface also has a side, one of the side is this dy and dz. So, this is also dy. So, this is a cube, okay. So, this side and this side are same, and this is dz, this is dz. So, let me take that out. So, we get something like this. Okay, we got something like this. This is our the same area. There is only difference in direction because it is the front surface of the rectangular box and the back surface. Both surfaces will have the same area, we know that. So, the area is same. Again, we have the old E, that is E is equal to E x into x cap plus E y into y cap plus E z into z cap. Now, and now we need the area, that is the ds. So, ds is equal to dy dz, that is the product simply dy dz. Now, what we need? We need the direction of that area. So, what is the direction? So, the direction of that area is, we know that this is the back surface and it should be outward, that means it should go away from that plane, that means it will be something towards here. Okay. So, from the back side it should be along the x cap direction. So, ds has a direction along x cap. Again we got the value of E dot ds, but there is a slight difference here. What is that? Let me check. Anyway, the product is same, that is we can product E dot ds, but the difference is we are evaluating E dot ds. Now, this area, okay, this E dot ds for the front surface we are evaluating the area at the front surface, that means x y z is the coordinate. Now, the only difference, the one and only difference with the back surface is we are evaluating the flux at a different point, that is a different plane. We got it by changing x to x plus dx. Other coordinates are same, this is y, this is z, here also this is y z, but x becomes x plus dx. Okay. Now, let us find out. Anyway, now we have E dot ds, E dot ds, that is for the back surface. I am writing it as back. So, back surface is equal to, just take the dot product. So, E x into dy dz. So, we have taken x cap, y cap, z cap, and all that product cancelled out. Okay. Now, we got this. Now, for we can take the front and back together. How? Here we have defined it for the back surface. Okay, back surface, it's okay. Now, let us take the sum of it to find the total sum of front and back. So, let us take it. Okay. For the back surface, we know that for the front surface, let me write it as E dot ds, that is E x dy dz, which is evaluated at which point? X plus dx. So, to denote back, instead of denoting it as back and front, I am denoting using this coordinate, this variation in that coordinate, that is x plus dx. So, this is evaluated at x plus dx. And now, what was our front surface? For the front surface, we had minus E x dy dz. Actually, I am taking the sum. So, minus, the minus was with the answer itself. Let me check it back. If you go back to the old slide, okay. Now, you can see that is for the front surface it is minus E x dy dz. We are picking it from there and adding it up with the back surface. So, let us go back to our derivation itself. Okay. Oh, that is it. Okay. Now, this is we are evaluating at another point. So, here we have a minus and minus into plus, we can write it as again a total minus. So, that is it. So, now we got it. This is evaluated at x. So, here one of the function I can call it this E x dy dz and Ex dy dz as a function f, okay, and this is evaluated at x plus dx and minus this is the same f, but it is evaluated at x. It is something like f of x plus dx minus f of x form. So we can use we can evaluate it using some properties of differentials. Okay, now we have to evaluate the sum. This sum is actually a sum, that is Ex dy dz evaluated at x plus dx minus Ex evaluated at x. So we have to find its sum. For that we are using some other technique we have already learned in +2 classes about differentiation, and we are taking a result from there. So for that we are representing Ex dy dz as f, but which is evaluated at a different point in the back surface, that means at the point x plus dx. Actually the variation is because of, not because of this dy and dz. Actually we are taking the value of Ex. So Ex has a particular value at x plus dx and another value at x. So this Ex, that is this Ex and this Ex are not exactly the same, because one is evaluated at the front surface and the other is evaluated at the back surface. That is why we represent it using some x plus dx and x here. Now we are taking it into the function, that is we are writing it as, let us write it as f of, so f of x plus dx minus f of x. It is something that kind of form, and we know that we already learned in the +2 classes, that is df by dx, that is the derivative of the function f with respect to x, is equal to f of x plus dx minus f of x divided by delta x or dx. You can write it as dx also. So dx. This is the definition of differentiation, the first principle of differentiation. And here we know that f is f. In this case, for our case, that is not just f, we have an e there, but e is not just a function of x only. There is x, y and z, and we took only two surfaces, that is the front surface and the back surface. When we go from the front surface to the back surface, the only difference is in x. We are keeping y and z constant. So there is another kind of differentiation by keeping any other two variables or all other variable constant, and we are doing differentiation only in one of the coordinate, then that is called a partial differential equation. So here also we are actually doing the partial differential equation. So we can, instead of this df by dx, which represents the total derivative, instead of that we can represent it as dou f by dou x, which is equal to f of x plus dx. Okay, also there is y, there is x, but they are all constant, there is no variation, minus so df by, so dou f by dou x is equal to f of x plus dx comma y comma z minus f of x, y and z. Now look at here, the only variable changing is x, and we are keeping the other two as constant. Here it is y, here also y, z, z. There is no change in that, we are changing only one. That is why it is called a partial derivative, and we can divide it with the dx. Now let us go back to our old function. What we were evaluating is that Ex into dy dz minus Ex into dx dy dz, but this is evaluated at x plus dx. Let me write it like this. So E into E evaluated at x plus dx. So, here you look at this is just neglect dy and dz. So, we can take it commonly outside, but this is Ex plus dx and this is minus Ex. Here also this is f of x plus dx and this is f of x, that is f of x plus dx minus f of x. Here it is E of x plus dx, let me change it, E at x plus dx minus Ex into dy dz. Now, this is exactly the same as the numerator. So, what is the denominator? We can cross multiply it to get f of x plus dx minus f of x is equal to dou f by dou x into dx. So, whatever be the function there, take the partial derivative of that and multiply it with dx. Here what is the function? Ex plus dx minus Ex. Instead of f we have here E. So, we can substitute instead of this dou f by dou x, we can put here dou E by dou x into dx. This is we got from here into the remaining dy dz. Okay. So, we evaluated for the front and back surface together and we got the sum as dou E by dou x dx dy dz. Now, what is this dx dy dz? Okay, we already drawn the cube. So, the cube had sides. So, we had a cube there and it had a side, one side is dx and this is dy and dz. So, it is a cube or a rectangular box and which had a side dx dy dz, then its product will be the volume. So, I can write it as dou E by, so dou E by dou x into d tau. So, we evaluate now, this is a sum of only for the first pair, that is a front and back surface. Similarly, we can evaluate for the front and back surface together, we evaluated this expression. Similarly, we can derive another expression for the top and bottom. Similar way we can define it for the top and bottom surface and we get it as dou z by dou z into d tau, and for the left and right surface we can define it as, or we can derive it as dou E y by dou y into d tau. So, these are the three sums or three pair of flux for all the 6 surfaces. So, we find it together so that it is easy to calculate, that is why we found it something like this. Now, we can sum it up into a single equation, that is we have, just go back, what we have to do, this is for the first 2 surfaces, that is front and back. So, we have to add plus this plus. So, this when we sum it up together we get the total flux over the 6 surfaces. Let us calculate that. So, that is the first, the total surface, for that we represent it as E dot ds, which is equal to what we got, dou E x by dou x plus dou E y by dou y plus dou E z by dou z, and we had a d tau common, that is taken outside. So, this is the result what we got. Okay, that is it. Now, we are going to represent it in a different way, that is we are introducing a new operator. So, let us go to that. We are writing it in this way. Let us check that, that is this is an operator, we will see what it is later, and we call it as a del operator, whatever it is, let it be there. Now, this is a vector x cap into dou by dou x, but it itself do not have any meaning. Why? You know, we know that d by dx, it do not have any meaning, it becomes meaningful when it got a function to act upon. So, that is why this is called an operator. So, this has to be operated on the whatever it is on its right side. So, we are taking a dot product. Here also you can see that it has 3 components, an x component, y component, z component. Already our E also has x component, y component, z component, and we are taking the dot product with this del and this E, and we are taking dot product. So, when we take the dot product, what we get, we know that is x into x that is 1. So, dou by dou x of Ex. So, this product will give you that. Now, the second product is this, that will give you plus dou Ey by dou y plus the third, the last one, that is dou Ez by dou Z. So, we can get back to that. That is, actually we splitted this single one into two part, and this we call this as a del operator. So, finally we get, or we can write it as del dot E d tau. So, this is for this del dot E, we call it as divergence, and we will see its physical meaning and everything later. So, for this time, just take it as a word, that is, this is called a del dot E, and we call it as divergence, and it has a very strong relation with its name itself, that is divergence. We will see that later. Now, here we did it for a small elemental area or elemental volume dx, dy, dz. What if it is a very large volume? So, then we have to integrate it, that is, we can write it as integral E dot d tau. So, now we want to go for a finite volume, that means we consider only an elemental cube, we need it for a very larger volume, then we have to integrate the right side also. So, we can integrate here also. So, here also we have to put an integral when it becomes a finite volume, that means integral E dot dA is equal to integral del dot E d tau. Okay. And this particular law, so before that let me write it down. So, this particular law is called, that is, here we are connecting a surface integral, that means here it is a surface integral and here it is a volume integral, we are connecting them together. Here the integral is over an area, and this is denotes that it is over a volume. So, we are connecting them together for the same function, that means we get, and we call that particular law as Gauss divergence theorem, and we are using this particular theorem to convert our integral form of Gauss's law to the differential form. Okay, let us see that. So, this is about Gauss divergence theorem, we will get back to that later, because we have to learn little bit deeper about this del operator and its other operations. So, let us go to the Gauss's law in the differential form. We already learned that phi is equal to 1 by epsilon 0 times q enclosed. This is the most simple form of Gauss's law, and we have converted it into the integral form like this, that is, integral E dot ds is equal to 1 by epsilon 0 times integral rho d tau. Okay, that is, this is the integral form. Now, we want to convert this into the differential form. How? Let us see. For that, we are using, here it is E dot dA, E dot dA and E dot ds are the same, no need to be confused. For area we use sometimes A or S, no problem. So, you can read it as ds itself, no problem, they are the same. Okay. So, now we know that this is integral E dot ds, and the left side of this is also the same. So, we can substitute it here, that for integral E dot ds we can substitute integral del dot E d tau there. So, when we substitute that there, what happens? We can see, so instead of this we substitute this. So, integral del dot E d tau is equal to 1 by epsilon 0 times d tau. That is, here the problem was the left side was a surface integral, and the right side was a volume integral. Now, we converted the both sides into a volume integral. So, removing the integral part, that is, this is the integral sign and everything, what remains is there is a del dot E and a 1 by epsilon 0 and a rho. So, we can equate them and we get what we get, that is, we can equate them, that is del dot E, that is this is equal to 1 by epsilon 0 times rho. Okay, that is, left side is called the divergence of electric field is equal to 1 by epsilon 0 times rho. So, this is called Gauss's law in differential form. So, this is what is called the Gauss's law Gauss's law in differential form. Okay, that's about it. And now we have the integral form as well as the differential form. Now we introduced to a new operator that is called a del. We will discuss about it. There is a particular operator, a vector operator that is called a del operator. It acts with the different quantities, and we will deal about it in the later sessions. And that's all about this session, and thank you.